So now I see experimental design, and we use this simple pendulum experiment as an example. So we use this ADDIE model. ADDIE model for experimental design. Okay. So what is that ADDIE model? ADDIE stands for these are the 5 steps, acronym for 5 steps involved in the process. So one is analysis, design, development, implementation, evaluation. So these are the 5 steps involved in designing an experiment. So I'm considering this simple pendulum equation, T is equal to 2 pi root L by G, and my aim is to calculate the value of G. So this is my aim. My aim is to measure the value of G at a given place using simple pendulum. Okay, so analysis part. So in the analysis part, what we have to do is we have to identify variables and constants. Okay, so what am I considering here? So T is a time period. So here first of all I have to identify the variables and constants. So what are the constants here? 2 pi is a constant. G is also constant in the given place. And what are the variables? L and T are the variables. So in these constants also 2 pi is a global constant and G is a local constant. So this G value varies from place to place, or it varies from varies for different experimental conditions. So for this particular setup and for this particular place, G value is assumed to be constant. So it is a local constant. And variables will be further classified into 2 types: independent and dependent variables. So what is happening actually? If you change the length of the pendulum, time period is changing. That is one statement. Another statement, if you change the time period of the pendulum, length is changing. I mean, which one is depending on the other one?
Time period depends on length.
So time period depends on length. So if you vary the time period, if you vary the length, time period changes automatically. So here this is the independent variable and T is the dependent variable. So when you design an experiment, we have to, independent variable will be under user control and dependent variable will be varying depending on that one. So so this is the basic analysis. We have identified the variables and constants. We have identified what is under user control and what is changing depending on that one. Okay, so now comes design part. So how to design that experiment? So we have to consider what? So we have to take the independent variable. So we have to take a set of values for independent variable, and we have to measure the dependent variable. So we have to vary the independent variable and measure the dependent variable and finally calculate the value needed to us. So G is what? 4 pi square L by T square. So this is how we consider or design this experiment. And so this is the basic idea. So we have to vary the length, measure the time period and calculate value of G. So that's all right. So now development. So what are the other conditions that we need to consider here? Either to improve the accuracy or to avoid errors. So what are the extra measures that we need to consider here? So the first condition here is theta must be less than 30 degrees. So that sin theta is nearly equal to theta. So this condition must be ensured. And what else do we need to consider here? So we are varying length. So we need a graphical confirmation also for this. So whenever you plot a graph, you have to take independent variable, the variable under user control to be along x-axis and the dependent variable should be along y-axis. And for our calculation, this dependent variable t is in the form of t square, so we require t square. Okay, so apart from other constants, we should get a straight line passing through origin. So here G is a constant, 4 pi square is a constant. So L by T square must be a constant for whatever value of L. So even if L varies, T also varies in such a way that L by T square should remain constant. Okay, so we should get a straight line passing through the origin. So that wherever you calculate L by T square, you should get a constant. So that is how designed an experiment. So now we need to develop it. So what are the developments? So one development is theta must be less than 30 degrees. And do we need any other repetitions or do we need any other additional modifications here? So let's say in the measurement of time period, do we need to avoid any errors is a matter of discussion now. So we are varying the length. So what are the conditions on length of the pendulum? Length must be measured up to the center of the bob, because we are assuming the pendulum to be a point object. So L must be measured up to center of the bob. Since pendulum is assumed to be a point object, the length must be measured up to the center of the bob. So, let's say if you want to keep 40 centimeters, and let's say the radius is 1 centimeter, then from here to here you have to keep 39, or from here to bottom of the bob you have to keep 41. So then only from the point of suspension to center of the pendulum will be 40. So if you measure up to the top of the pendulum, you should subtract the radius, or if you measure up to the bottom of the pendulum, you should add the radius. So this is the second condition. What about other ones? So now, so this is the restriction on measurement of the length. So next one, measurement of time period. So how to measure time period? What is time period?
Time taken for one oscillation.
Time taken for one oscillation. So where shall we count? Where shall we start our counting? Let's say the pendulum is starting from here. It is going to one end, reaching the center, going to other end, reaching the center. So if you start from the center of the equilibrium position, then you have to count. Let's say 0. It goes there, comes here, goes to the other end, again comes here. Then it will be 1. Again 2. So like that you have to count. Otherwise, if you start at the end, what happens? It should go to the other end. 1, 2. So like that you have to count. So now, what are the problems that can arise in this process? So our aim is to measure time taken for one oscillation. So where shall we start counting 0? Is it at the end or at the middle or at this end? Which is a better choice?
Mean position.
ఎందుకండి?
Amplitude change of oscillation.
Okay. So if it is the extreme point, what happens? The pendulum reaches there, stops there for a while and comes back. And we don't know at what time are we starting counting. I mean, we're not exact whether we're counting at the entry time or halt time or departure time. So there is a time lag at the extreme points. So whereas at the equilibrium point, it runs very quickly. So you'll avoid that small error that comes at the extreme points if you start counting at the middle point. Right? So you must ensure, I mean, if you start counting at the extreme points, the problem is there is a time delay. One, the pendulum arrives at the extreme point, stops there for a while and turns back. So we don't know when are we stopping that stop clock or when are we starting that. So there will be a small delay. To avoid that, better is to start counting at the middle point. Okay, so next issue. Let's say my aim is to count for one oscillation. So goes there. So let's say it takes 1.25 seconds. Let's say 1.2 seconds. And my stop clock has only seconds division. So after 1 second, it goes to 2. What to do then? How to avoid? So my clock will show either 1 or 2. If I am quick enough, I'll stop at 1. If not, it goes to 2. So I may not get the exact value. So how to overcome this problem? The problem is my clock least count is less than the accuracy that I require. So it is a problem with the measuring device. So how to avoid that? So when you cannot control with the accuracy, you try to scale up the experiment. try to count time for 10 oscillations. What would it be? It will be 12 seconds. Right? So if I scale up the experiment and I start counting time for 12 oscillations, 10 oscillations, I should get 12 seconds as a result. Right? So I'm avoiding the error by scaling up.
Oscillations.
So why am I scaling up?
To avoid accuracy.
Because the least count of the measuring device is not matching with the accuracy I require. Right? The least count of the device is 1 second, but the accuracy I require is 0.1 seconds. So to avoid that, I am scaling up the experiment to 10 times. So I'll measure the time period. So L T for 10 oscillations. Okay, and let's say if the time period is 12.5 or 1.25, let's say. What happens here? So that's okay. Okay. Okay, keep it at 1.2. So I'm repeating it for 10 times to avoid to acquire the required accuracy by overcoming the least count of the device, measuring device. So scaling up is to overcome the least count discrepancies. Okay. So I scaled up. Then do I need to repeat it? And why do we repeat it 2 times and take an average? Why do we need to repeat it? Repetition of experiment is to avoid human errors. So our exact measurement should give us 12 seconds. But so when I counting it by the end of the 10th oscillation, I have to see it. So after I see that, I should get a signal to my finger. Then only I'll be able to stop that. So there is a small delay. So in the time, during that time, my clock may go to 13 seconds. I mean, immediately after seeing the result, I may not be able to stop the clock. There may be a small delay. So during that time, our next count may rise. It may go to 30. And sometimes, since I got a clarity that I am delaying, I may quickly stop it even before I see the result. Right? Then I may stop at 11 sometimes. So to avoid these human errors, I'll repeat the experiment and take an average. Okay. So repetition of experiment is to avoid human errors, and scaling up of experiment is to avoid least count discrepancies in the measuring device. So I did that, and T is equal to T10 by 10. Then G. So this is how I developed the experiment. So I have analyzed the equation and identified what are the variables and what are the constants, and what are independent variables and what are dependent variables also have identified, and analysis part is over. Then I started designing an experiment. So I have varied the variables and user control, and measured the values of dependent variables and calculate the value that I need. So this is how I designed an experiment, and I plotted a graph for L versus T square, because that is the numbers that exist in this equation. Then I developed it depending on the experimental conditions. So this is the condition I'm imposing, because the equation I'm considering here is an approximate equation. This is not exact equation. So this is considered by replacing sin theta with theta, but actual equation is what? 2 pi root L theta by G sin theta. So instead of this equation, I'm considering L by G. So I have to consider that condition also. Then I have to look for the design part. So how to measure L, how to measure T, what are the possible errors and how to avoid them need to be taken care in the development part. So I have considered the possible errors in the measurement of L, and I'm ensuring how to measure the length up to center of the bob. I'll measure up to bottom of the bob and subtract the radius, or I'll measure the length up to top portion of the bob and add the radius. And coming to time period, depending on the least count of my measuring device, I'm scaling up the experiment, and then to avoid human errors, I'm repeating the experiment and taking an average. So with that, development part is over. Then we implement it and fill the table. Further comes the analysis part. So once you implement the experiment, you'll fill the table and get some value for G. So now evaluation part. So we'll try to confirm whether the obtained results are good enough for the accuracy. Okay. So here evaluation part, we consider the graphical evaluation. So let's say our L by T square is 1. Let's say for the time being this is 1. So that when you plot a graph for L versus T square, for each value, let's say for 40, T square must be 40, for L 50, T square must be 50, for L 70, T square must be 70. So like that you have to obtain your values. So if at all, if that L by T square is 1. Okay, so now we have conducted the experiment with all possible safety measures or whatever conditions we have developed. And now let's say some user missed this rule that length must be measured up to the center of the bob, and somehow he or she considered the length 40 centimeters up to here. Okay, so measured the length 40 centimeters up to here. and he wrote 40 in the table. What value of t square will you get?
39.
So measured 40 centimeters here, so you would get 41. Actual length is 41. Measured 40 centimeters up to here. So actual length is 41. So should get 41. So for 50, you get 51, 60, 61, 90, 91. So what happens to the graph? The graph shifts up. So for 40, you'll get 41, 50, 51, 90, 91. So graph shifts up when this is original, expected, and this is measured. So when you see the experiment, when you vary the length, time period also increases. Square of the time period increases linearly. So that part you can confirm it by seeing the table, and results also may get some numbers, that is also valid. But this kind of error can be identified only through graph. If the graph or the line is not passing through the origin and if shifts up, that means what? The user has underestimated the length. Actual length that he kept was 41, but he wrote 40. So this is when the graph shifts up, it is underestimation of length. Okay, so what if he measures 40 up to here and he writes 40. So what you get is for 40 you get 39, 50, 49, 90, 18. So the graph shifts downwards. This is original and this is observed. So that arises because of overestimation of length. This is underestimation of length. So actually he kept 39 centimeters and wrote 40. So it is a overestimation of length. So when length is overestimated, the graph shifts downwards. Okay. Yes, then what about errors in time period? So these are the mistakes actually. These are all errors. Whatever human error or least count errors, these are all errors. These are mistakes. I mean, this can be implemented, but by mistake we have not implemented it. Measuring length up to center of the bob is possible, but by mistake in understanding the definition or mistake in understanding the concept, we have implemented it wrongly. So that kind of errors, I mean that mistakes can be identified only through graph. So what about time period? So if we overestimate the time period, what happens? I mean, how does it reflect in the graph? So let's say our clock, instead of counting 0 in the beginning, I start counting 1. So let's say I count my starting count as 1, 2, 3, 4. So by the time I count 10, actual count was 9. Means what? I am overestimating the time period. What happens? So I kept the length 40. I counted for 10 oscillations. But actually I have counted only 9. I counted 9. So what number will I get here at time period? I get a lower number. I get 38. Right? And for 50, I get even a lower number. For 90, I get, because I am squaring the time. So I'm subtracting one count. Actually I'm counting 9 only and I'm squaring it. So error will be keep on increasing. Here the error is only 2 units, here it is 4 units, here it is 8 units. So what happens? Let's say this is the original graph. This graph now falls downwards. So this is because of overestimation of time. The same way, instead of counting 0, otherwise after one oscillation I count 0. Somebody may do that, right? By mistake. So what happened? This is the starting point. After one oscillation I started counting 0. So I'll actually count for 11 oscillations, but I write my report as 10 for 10 oscillations. So when the reports are underestimated, what happens? For 40 I'll get 42, for 50 I may get 54, for 90 I may get 108. So like that the error keeps on increasing. So this is because of underestimation of time. So somehow somebody does an experiment and got a graph like this. What kind of errors are there? What kind of errors are there and how to correct them?
Underestimation of length.
It is overestimation of length. He is measuring the length up to bottom of the bob. So for overestimation, graph shifts downwards from the horizon. So there is a shift down from the horizon and slope is increased. So there is a overestimation of length and underestimation of time. Okay. So like that, just by seeing the graph, you can understand where are the mistakes, what are the possible mistakes, and how to avoid them can be identified from graph. Okay. So from there you can calculate L by T square and get the value of G. So that is why graph plotting is more important. I mean, you will be able to identify mistakes, I mean, which cannot be understood. Mistakes are, I mean, by ignorance only, right? Most often. I mean, misunderstanding of the concepts. So that can be corrected only through the graph. So now comes the case. So all this experiment is performed with the approximate equation. What happens if I rise this? Instead of 30 degrees, somebody stretched this to 60 degrees.
Temperature increases.
So what happens? So the actual equation is what? T is equal to 2 pi root L theta by G sin theta. So this is the equation. So what are we doing here? So here for small values of theta, for theta less than 30 degrees, theta and sin theta will get cancelled. But we are now stretching it to 60 degrees. So what happens? So what did we see? Here theta is larger than sin theta. Let's say for 90 degrees, what is that? 1.5 was theta, sin theta was 1. So like that the values will vary. So time period increases when theta is very large. Okay. So time period increases, and calculation of g. For the calculation of g, what are we doing? We are taking 4 pi square L by t square, and we are substituting the high projected value of t in the denominator. So ultimately, the value of g that you calculate using long stretched pendulum will fall down. So let's say as a function of theta, so for small values of theta, g value remains same, let's up to 30 degrees. Beyond 30 degrees, this value starts reducing. So this is experiment. So this is the result you get. Okay. So that is the case. But what is that actual formula says? G is equal to 4 pi square L theta square by T sin square theta. T square sin square theta. So actual formula is G is equal to 4 pi square L theta square by T square sin square theta. Right? So when sin theta value is substituted, what? Theta and sin theta. What is happening here? So when you consider larger values of theta and sin theta, what happens? This numerator increases and g value increases. So if you just consider that direct substitution of theta by sin theta, it looks like g value increases, but when you do the experiment, g value decreases, because you are not measuring the value of g from the experiment directly. You are measuring the time period and substituting it to calculate g. You are calculating the value of g and you are measuring the value of t. So with theta by sin theta, when you measure the value of t, t increases, and when you substitute it back into g, g value decreases. But if you just see the formula, G also contains theta by sin theta. For larger values of theta, G value increases. Right? So that must be clear about. You are not measuring G, you are measuring the time period and substituting some equation and calculating G. G is being calculated and T is being measured. So because of that, when you do the experiment, G value reduces for larger values of theta. And if you see the formula, G value increases with larger values of theta. Right? So with that, ADDIE model for experiments is over. You can design any experiment by taking any other equation.